Hey everybody, welcome to week 4 of Computers and Computations here at the University of Constance. Last week, week 3, we talked a bit about the notion of Turing computation, how it's a really flexible notion of computation. So there's this thing called a universal Turing machine, and if I feed it the code for another machine and an input for that machine, then it'll go ahead and do what that machine would have done. So it's a hugely flexible notion of computation. This week, we're going to see the first few examples of severe limitations to the notion of Turing computation and exactly how this goes down. So hope you enjoy the talk. So here we go, talking about the halting problem. Now, I might be talking a bit quietly this week because it's a bit late here and everybody else is asleep. So I'm going to be giving this talk in somewhat hushed tone. So I hope everyone can hear that and it doesn't bother you guys too much. First off, let's recap some of the key points from last week. So last week we talked about how certain problems or functions could be Turing computable in terms of being computed by a Turing machine. So one of these machines that has a tape and a head, and it can write 0, or it can write 1, or it can move right, or it can move left and transition to a different state. And critical in this discussion was the point that we could encode a Turing machine M by a natural number, right? This corner quotes M down here. And then this can then be used as an input for other machines. So the good example of this was the universal Turing machine. And the universal Turing machine, if I've got a tape here, takes a code of a machine M here, an input X for M, and then computes what M would have done on X. So we can code up machines and feed them as inputs into other machines. Now, once we have the ability of coding up machines and feeding them into other machines, we can have the following general idea, right? So I can design Turing machines that will check other programs, other Turing machines, for certain properties on certain inputs. So, for example, I can have a machine, or I can try and design a machine that will look at the code of another Turing machine and try and decide if it has less than n many states for some particular natural number of n, right? So that's a sort of simple thing we might check for. But more interestingly, we have the idea that we could feed in machines into other machines that will check them for bugs, right? We'll check them for problems or undesirable behaviors. And this is exactly what the halting problem is going to begin looking at. Okay, so that's the idea. We want to be checking Turing machines for certain behaviors by feeding their codes into other Turing machines, right? Now, here's what we'll discuss in the main body of this video. So firstly, we'll discuss exactly what the halting problem is. This is the problem, roughly speaking, of designing a Turing machine to check when others halt versus go into some infinite loop. Then we'll talk a little bit with that. This is just going to be kind of discussing what the halting problem is. Then we'll discuss the fact that there are some functions that are not computable. We'll discuss some simple ones. Section 3 will show that the halting problem is not computable. Section 4 will talk about the relationship to the Untitled problem. And section 5 will talk a little bit about a theorem called Rice's theorem. This is intimately related to the halting problem and has several very interesting applications. So in section 5, we'll discuss Rice's theorem. Good. So we want to design a Turing machine or various Turing machines that can check an arbitrary other Turing machine for various kinds of problem, given some input n. So one kind of problematic behavior is failure to halt. So suppose we have some Turing machine T, and we've got some input X for T. Well, what we want is that T, when it runs on X, if we're trying to compute some function f, and fx equals y for some particular y, we want T to go ahead and do its computation. It'll move right, it'll move left, it'll write stuff to the tape, and then at the end of the day we want to have y left on the tape. We want T to move to the left-hand most bit of y and then halt, right? What we don't want is T to just, when it starts operating on our original input X, we don't want T to just run off endlessly to the right or endlessly to the left, or get stuck into some dithering kind of loop where it moves right and then left and right and left, but will never actually ever halt, right? We want it to compute the function f we were talking about. Okay, good. So what we really like is a Turing machine that can tell me, given a particular other machine, whether it halts or not. So we can define the halting function as follows. Okay, it's a partial function. It operates on pairs of natural numbers, and it goes into the natural numbers. Really, we only care about 0 and 1 here. We can define it as follows. So where M is a particular code for Turing machine M, we want H to give us a 1 if M halts on N, and not otherwise. Okay, and we'd love to design a Turing machine to do this. Now, before we go on, just note that H is a perfectly well-defined function, right? There is a fact of the matter whether or not a particular machine halts on a given input. The question we're asking is H computable by some Turing machine? Good, so now we can talk about the halting problem for Turing computation. We can simply define this as, is there a Turing machine computing the halting function? So, is there a Turing machine that when I feed it another Turing machine and an input will output 1 if that machine halts on X and 0 otherwise? Now, as I said in the introduction, we're eventually going to show that this function is not computable. But let's just talk more generally about the notion of uncomputable functions. So, not every function from n to n is going to be computable. There's just too many of them. Okay? Now, to see this, think of a particular function as from the natural numbers to the natural numbers as an infinite sequence. Okay? So what a function from the natural numbers to the natural numbers does is it says, depending on whether you start with 0 or 1, so it says in the 0th place we've got a number, say the number 500. In the first place we've got a different number, right? We've got 2, let's say, it doesn't matter what it was. In the second place, we've got 999, let's say. In the third place, we've got 17. In the fourth place, and so on, right? So this function is telling us what numbers are mapped to what other numbers, but you can think of it as this big long sequence. So in this case 500 to 999, 17, etc. off into the distance. Now, without loss of generality, we can think of these as in binary. So you can just think of a big long sequences of zeros and ones, and each particular function from the natural numbers to the natural numbers just giving you a big long binary sequence. Okay. Now, you can show, and this is a theorem of Cantor, that there's just way more functions from natural numbers to natural numbers than there are natural numbers themselves. Okay, so how do we see this? Well, assume that we had such a function, right, that would list all the functions from natural numbers to natural numbers by taking a natural number and mapping this in a 1, 1 and onto way. So it pairs up every natural number n with some function fn, and we get all the numbers, and we don't map any two natural numbers onto the same function. Okay, that doesn't happen either. Okay, so if you have this sort of situation, we can write this down in a grid, right? So we have our f1 here, right? This is our first function, and this is a big long infinite sequence, as we discussed, could be done up here. Okay, f2 is here, right? f3 is here. This is just some other sequence, and I'm going to show you that there's a sequence not on this list. So I use here a method called diagonalization. So what do? I define the following function, right? It takes each natural number, right? And it gives us a 0 if the value of the n-indexed function at n is 1, and it gives me a 1 otherwise. So what's this going to look like? Okay, so on the grid, I look at f1 and I look at what is in the first place of f1, and it's a 0. Okay, so I say that d0 is 1, right? Okay, I look in the cell d1, since we're operating only with the numbers from 1 upwards, but it doesn't matter for these purposes. Okay, so then we look at f2, okay, we look at the second place, right, and we know that that's a 1, so we go to 2, and we change that to 0, right, and similarly for d3, right, there's a 0 there, so d3 will be 1. And so what I'm doing is I'm ensuring that the sequence defined by this function d here differs from each one of these f's in the nth place. So it's going to have f. It's going to have in the first place 1. It's going to differ from f2 in the second place. It's going to differ from f3 in the third place, f4 in the fourth place, and so on. Right? So there's no function that just pairs up one-to-one the natural numbers with the functions from natural numbers to natural numbers. Have a think, given the coding of Turing machines before the next slide, why that means there must be some functions that are not computable. Okay, so here's the answer why. Our coding of Turing machines we discussed last time identified a unique natural number for each particular Turing machine. So if every function were Turing computable, we would be able to enumerate the set of all functions from n to n just using our Turing machine enumeration. So there must be some of them that are missed. Okay, so here's an example of one. Here's the diagonal function. So let f from n to n be defined by taking n and mapping it to the nth Turing machine, right? Where the nth Turing machine is the nth Turing machine in our coding of the Turing machines, right? And we'll write the associated function here as fn, right? And then dn is just going to be 2 if and only if fnn is defined and equal to 1, and 1 otherwise, right? So this function can't be a computable function because it differs from every computable function precisely on the nth place according to where it appears in the enumeration of our Turing machines given here. Good. So we know that there's some functions that can't be computable. So now let's see that the halting problem itself is not Turing computable. Okay, now I'll suppress some of the details here. You can go to chapter 4 of Boulos, Burgess and Jeffers if you want full proof with all the details, but we'll get a feel for the structure of what you do. Okay, so we're going to assume for reductio that we have such a Turing machine computing HMN. So we do actually, let's assume that we have such a thing, right? Okay, so the first step is we design a copying machine, TC, that takes an input M and produces M after M on the tape. Okay, so it takes any input we like M and it's just going to copy the input. Okay, so a join TH to TC, i.e. you just put down your copying machine, TC, and then you take TC's output and feed it into TH, right? So a machine that runs TC first and then runs TH. So what's this machine going to do? Well, it's going to copy, given an input M, it will just copy M on the tape, and then it will run a TH program on that doubled input. So it's going to compute the function HNN given an input N. So let's write sort of putting together two machines with this concatenation symbol here. Okay, now let's design another machine. This is step 3, called a Gargamel machine. So Gargamel, from Smurf fame, just tries to ruin everything all the time. So we could also have called this a spoiler machine if we'd wanted to, or a ruiner machine or something. So what does TG do? Okay, so given an input of 0, it's going to halt. Okay, so all that TG does is you give me an input of 0 and I exit fine and halt. You give me an input of 1 and it runs forever. And there's a number of ways it can, we can have it do this. We can have TG just sprint off to the right or left, depending on our preference. Or we could have TG just dither backwards and forwards, or just repeatedly print a 0, delete it, print a 1, delete it, print a 0, then delete it and print a 1, and so forth. Okay, now what are we going to do? Well, we put TG on the end of our copying machine conjoined with our halting machine. Okay, so we're going to have the program that copies an input first, sends it into the halting machine, right? And then once the halting machine has delivered its verdict, we feed that into the Gargamel machine, okay? This is a contradiction. There can be no such machine, okay? And so by reductio, this doesn't exist. And so HMN is not Turing computable, okay? Why is this a contradiction? I've given the reasoning on the next slide, but given the kind of self-referential paradoxes we get in philosophy, things like Russell's paradox, maybe you want to have a think about it before the next slide. So you can pause here. Good, so what's the contradiction? Well, we're going to do the typical self-referential trick that pops up over and over again in philosophy and logic and apply the machine to itself. Good. So we're going to feed, remember we've got this box, I've got our copying machine going into our halting program that's then going into our Gargamel machine, right? And what we're going to do is we're going to feed the code for this machine into itself. Okay. I'm going to give that as an input. Okay, now question. Does this machine here, does it halt given the code we fed in? Well, suppose it did halt. Okay, then we know by the definition of the Gargamel machine, remember this just takes a naught and it halts on naught or spins off given a 1. But then we know that TG must have received a naught here, right? But if TG received a naught, right, then TH must have outputted a naught, right? But that means that this machine here, right, didn't, this whole machine here, sorry, on this input didn't halt, right? So that's a contradiction. The halting program tells us that it didn't halt, but then the behavior of TG, given what the halting program must have outputted, tells us that it did halt. Okay, right, so contradiction in this case. Okay, so suppose it didn't halt then. Okay, well, then we know that TG must have received a 1, right? Because that's when TG goes off and doesn't halt, right? But if TG received a 1, right, then TH must have output a 1. But TH only outputs a 1 just in case the machine halts on this particular input. So that's also a contradiction. Okay, so whatever we think the machine does, we get a contradiction. Okay, now let's discuss some payoffs of the halting problem, or this resolution of the halting problem. So the first is going to be the Entscheidungsproblem. So recall that this is the problem of given a first order formula phi, right? In this case, a code of phi that we input into a Turing machine. Do we have a TE that when fed this code of a formula will output 1 if phi is provable, phi is a sentence of first order logic, or 0 if there is no proof of phi, right? Good. So let's talk about the rough idea of what we're going to do here. So we're going to show that or describe how, I should say, the full proofs can be found here. They're a little bit involved, but it's interesting to see the rough idea. But we're going to talk about how if you had this machine TE, what this machine TE would do is it would allow you to produce a machine of the form TH computing the halting function. Okay, so here's the rough idea. So we're going to start by describing a particular effective way of representing Turing machines and their behavior using sentences of first order logic. Okay, so what we're going to do is we're going to encode Turing machine behavior into some sentences of first order logic. And in particular, it's important to get sentences tau MW that represents the machine M and a particular input W, and a sentence alpha MW that expresses the idea in terms of logic that M halts on W. Now, once you've set up all these logical details, you have these sentences tau and you have this sentence alpha, what you then go on to show is that if this sentence is provable, right, in particular that in logical terms that M is a machine and W is an input for M, and this implies, this is in logic, right? This is not talking about actual behavior of Turing machines. Then alpha of M and W, where this is the halting sentence. This holds if and only if M, the actual machine we've encoded up into logic, does halt on input W. Okay? So what you then have is that if you had a solution to the Entscheidungsproblem, right, in particular, you could always check whether this sentence was provable, then you could actually find if the machine did halt on input W, and in fact it goes vice versa. Okay, and just to say a little bit about what the language has, it has things like predicates for states, predicates for alphabet symbols, a constant for 0, function symbols for left and right, and a predicate for before and to the left. So before in terms of how the machine develops, and to the left in terms of the contents of the tape. And then axioms include axioms describing basic operations on numbers, input configurations, and transitions between different states of the Turing machine. So this is what's contained in the logical system one would try and use to prove this sentence. This is a fairly standard axioms, and part of what you have to do is show that this is a faithful representation. Okay, so this shows you that the Entscheidungsproblem is not solvable, because if we had a solution to the Entscheidungsproblem, a computable solution, that is, then we'd also have a computable solution for the halting problem. And the key notion at play here is the notion of a reduction. So this is a very important notion in theoretical computer science. So we say that B reduces to C if whenever you have a solution to C, you can then transform it into a solution to B, or compute a solution to B in some relevant sense. Okay, so this is the strategy of what one does. You take a solution for the Entscheidungsproblem, or a putative solution. You show that it can be transformed into a solution for the halting problem. Because you know the halting problem isn't computable, you also know that the Entscheidungsproblem is also not computable. Okay, so the resolution of the Entscheidungsproblem gives us some pretty profound philosophical and logical implications. It's not the case that we can just determine whether or not a sentence is provable or not by running some algorithm or other. And there's clear connections with the philosophical literature here. So if you think that in principle we could prove or refute any mathematical principle, let's say, or mathematical axiom, then you have a question to answer of how could this be done? Well, it couldn't be done computably. So how does that link to philosophical questions surrounding things like the nature of the human mind and so on? We'll discuss this a bit in future weeks. But are there practical implications of the halting problem? After all, computability is supposed to tell us about computing devices that are tremendously important. And I think here there are some practical implications. So the first thing to note is there's no such thing as a perfect debugger. What does a debugger do? Well, it's a program that if I feed it some code or another Turing machine, it's going to tell us if there's errors in the code. Well, assuming that you think that the program not halting on a particular input is a kind of error, and that seems pretty plausible, then you can never design a perfect debugger, because it would have to also solve the halting problem for you. Okay, so this is pretty useful information if you're, for example, a software engineer. But it turns out we can go a lot further. And critical here is something called Rice's theorem. And I wanted to throw out a big shout out here to Joey Aramondi, who pointed this out to me. He's got a really fantastic, concise answer to why the halting problem is important on Stack Exchange, and I'll leave a link to that Stack Exchange question in the description. Okay, so to set up Rice's theorem, we're going to need an extra definition. And thus far, we've been talking primarily about computing functions, right? So I have some function fx, and it gives me some value y for any particular x of the required kind. And I want some Turing machine that's going to run on input x and give me output y. This is what it means to be Turing computable, right? But we can also talk about sets being computable too, right? So a set B, this is just some set of problems that can be encoded into inputs into Turing machines, is computable just in case there is a Turing machine that computes its membership. So what does this mean? If you give me a possible instance of the set, MB will halt with 0 if X is not in the set in question, and the Turing machine will halt with 1 if the input you give me is in the set in question. So this is the sense in which a Turing machine can compute set membership, and sets can be computable or not. Now, with this idea of sets being computable in hand, we can talk about what Rice's theorem says. I won't give a proof of it here, but you can see the open logic text, in particular chapter 28, section 21 for a proof. So let's let F1, F2, F3 and so on be the enumeration of computable partial functions determined by the enumeration of Turing machines, okay? So I've got my enumeration of Turing machines given by their codes, and the first one to compute a partial function in my enumeration, this will be given F1. The second one that computes a partial function, this will then give me F2, right? F3 and so on. We can now state Rice's theorem. So let C be any set of partial computable functions, right? Any set, whatever, okay? Then this particular set A, in fact, the set of all the indices of Fn, right? So this is going to be a set of numbers, right? Corresponding to the indices that we have in our set of partial computable functions. If this set is computable, okay? So if we have an algorithm that tells us, or a Turing machine in this context, what indices are in A, and hence what functions are in C, then if A is computable, then either our initial class of functions was none of them or all of them, i.e. the only computable classes of functions in terms of the index sets we talk about are trivial. It's either nothing or everything. Okay, so why is Rice's theorem important? Okay, so the first point to note is that a standard proof of Rice's theorem is exactly this method of reductions that we talked about before. So what you do is you show that if I had the computability of such an A, that's an index set for a bunch of functions, then the halting problem would also be computable. And so these functions can't be computable. Okay, these classes of functions, can't be computable. Okay, good. So, I mean, this is just another example of a theorem you can get from the halting problem. But it runs a lot deeper than this. Okay, so some Turing machine behaviors can be computable, such as, does this program have more than n many states or less than n many states? So very specific questions about Turing machines can be computable. But what Rice's theorem shows is that any non-trivial question about program behavior, okay, so such as what functions different Turing machines compute, i.e. different choices of C, any way of grouping together the functions that different machines compute, if such a question is computable, then it just gets you either none of the functions or all of the functions. So it turns out to be a trivial question. concretely speaking, this has lots of practical consequences, and I'll give some concrete examples on the next slide. But any program analyzing the behavior of other programs will either have false positives or false negatives. So it's going to either classify too many programs or too few. So this pops up in the computer science literature as programs that analyze other programs and bar some safe behaviors are often called sound, and programs that allow some unsafe behaviors are often called unsound. And this is a real problem that can't be got around when you're having programs to analyze the behavior of other programs. It's just not possible to get every case right for a wide variety of questions. So here's two problems that I was directed to of contexts in which the halting problem pops up in a practical sense. So the first is, suppose we've got an antivirus program, right? Now, what does an antivirus program do? It checks that other programs are not going to write to sensitive files in some context, okay? Now, what might you think? Well, I'll go and I'll look for instructions to write to, particular files that they shouldn't be writing to. Okay, but maybe it's the case that all execution paths that would do this have infinite loops before them. So there is some execution path here that at some point writes to some sensitive files, right? But it could be that all the paths that do this in the execution of the program, before them, the program gets stuck in an infinite loop. So I have a particular program, let's call it P, and it acts on some inputs, right? But in all the cases where it would go on to do this, so to say, it doesn't actually. It gets stuck in an infinite loop before this and fails to halt. So if I could tell you exactly when a program is going to write to sensitive files, I could within that tell you when the halting problem is solvable or not, because I'd have the ability to differentiate the instance where the program just writes to sensitive files from the one in which the program would write to sensitive files but gets stuck in an infinite loop first. Okay. Second example, we want to check if two programs do the same thing. So, for all intents and purposes, they're identical in some sense, right? They have the same behavior, let's say, on the tape, okay? Or in terms of what they write to the tape. Okay. So suppose you have some code, you change it, and you want to know if you change the behavior of the program by changing the program. Okay, so I want to know, did I make it do something different by changing the relevant code? Okay, this would let us solve the halting problem. Well, why? Well, I can just give you a trivial looping program, and then if I had a program that would compare any two, I can compare any program to it and solve the halting problem, right? Again, it's this method of reductions that pops up in both these cases that tells you that the halting problem is going to crop up in this context. Okay, so that's all for this week. I just want to conclude with sort of introduction to think about what we might do to respond to the halting problem. So the halting problem shows that there is no computable way of solving a really broad class of philosophical and practical problems. Okay, it's a lot broader than you might think when you just see we want to detect that whether or not programs halt. Turns out that this property is encoded into an awful lot of other problems, right? Or it is reducible to a lot of other problems, and they're reducible to it. Okay. Let's just remember with something we started with when discussing the halting problem, though, is that there is a fact of the matter about the values of the halting function. There is a fact of the matter, given a machine M and an input X, whether or not M halts on X, right? Now, you might think, how do we respond to this problem that there's a fact of the matter about what the values of the halting function are, and how we respond to this in terms of a theory of computation. So we won't go through any here. I think you guys have listened to enough, but I want everyone to think about how might we try and respond to the halting problem. So what might be some ways we try and get around it? Obviously, these won't be computable ways. Or do we just accept it as a fact of life and accept some restricted notion of what we want out of this kind of program analysis? Good. Thanks for listening, and catch you soon.